Yes, I hope all of us are doing fine. My name is Ernest, and this Ernest is Sciences and Mathematics TV channel. In this particular discussion, we're going to look at a second bit of the representation of a harmonic oscillator or a diatomic molecule in form of an harmonic oscillator in terms of a partition function. And of course, in our last discussion, I had explored various relationships which, of course, are arranged between the vibrational frequency, the force constant, and that's of course the force constant of a diatomic molecule being considered in terms of course, this harmonic oscillator. Now, in this case, I had mentioned also the concept of a reduced mass, and we had come up with a specific description of this specific concept of vibrational frequency given in terms of omega. And we said omega is equivalent to 1 over 2 pi and the root of k all over reduced mass. And I said that basically the aspect of omega implies a vibrational frequency, and then we had k, which represented the force, basically which referred to as the force constant. And then lastly, we had considered the aspect of reduced mass given in this specific notation. So in this case, the relationship between the three gave us the aspect of this particular vibrational frequency. And for an harmonic oscillator, of course, we said that we can borrow from this specific concept and of course describe a diatomic molecule force, which is going to be beta. In this case, we had used a heteronuclear diatomic molecule and given it in terms of that specific representation. Now, for these two specific atoms, we had given them a mass of 1 and 2, and we said that, of course, we can describe the rotational aspect using, of course, this bond length and then the distance between the center of mass to those various atoms which we had given. And of course, that one gave us an aspect of describing this particular aspect of the moment of inertia, which we said, of course, for rotational aspect, we're going to need the moment of inertia and the distance from the center of mass, of course, to describe this specific aspect. Now, for rotational, of course, for a rotational partition function, then therefore we're going to look at the rotational description of this specific harmonic oscillator. And in this case, of course, we're going to find this representation of energy of a harmonic oscillator from the Schrödinger's equation, which is going to give us, of course, the set of equally spaced but singly degenerate levels, as I'm going to, of course, as we had illustrated in our last discussion. Now I'm going to put a link of that specific video in our description box. And of course, this specific type of degeneracies given us a general representation for energies, which were basically vibrational or allowed vibrational energies given in terms of un. And then we said that this can be given in terms of n plus a half h omega. Now, in this case, we have decided that n basically represents what we refer to as vibrational quantum numbers, which are going to be given in terms of ranging from 0 to positive infinity, given in that specific order. Now, basically, this one gave us a way of describing this specific vibrational or allowed energies in a vibrational harmonic oscillator, or a vibrational mode of this, or a vibrational description of this particular harmonic oscillator. Now, we came up with a general description which basically related the molecular vibrational partition function, and of course we achieved this through the substitution of this specific vibrational description of internal energy in the general equation of our partition function. Now, we have said that basically we're going to represent this specific partition function in terms of QV, which basically was a summation between n equivalent to 0 to positive infinity, and this of course is going to be given in terms of the exponent of so we're going to do a substitution of the negative values of this specific description for energy, and of course this was given in terms of h omega all over kBt given as such. So this gave us a general representation for the partition vibration, or the molecular vibration partition function from our last discussion. Now, today we're going to look at a way of representing this specific aspect of the partition function, and of course this is going to entail the concept of vibrational temperature. Now in this case, the vibrational temperature is going to take account of some specific terms within this particular formula, which are going to exploit the usage of the Kelvin scale. And of course, it's going to yield the aspect of what we refer to as a vibrational temperature. In our last discussion, we had looked at the concept of rotational temperature. And in this case, for vibrational temperature, we are going to represent it using theta as subscript v given as such. And this is going to be described as the ratio between h omega and kb given as such. So therefore, we're going to look at our general case for various aspects of this specific range of quantum numbers, and see from the first, from that specific description of the potential energy curve at given a various range of this specific energy in terms of n. And therefore, we're going to use for various ranges of n, we're going to come up with a specific equation which is going to describe the summation of all this range of energies for 1, 2 onwards as such. Therefore, we have said that taking note of this vibrational temperature, and therefore we're going to have this one given in terms of QV. So we're going to do various substitutions of this specific summation for the values of QV, whereby we're going to have it as an exponent of so the first term is going to give us negative vibrational temperature over 2T, and then we're going to have the negative term giving us a plus. So it's going to be a summation of these specific temperatures, as I've said. So we're going to have the second one giving us the exponent of this specific 3. This is the vibration, of course, vibrational temperature, and this is going to go on according to that potential energy, of course, curve which are given. And the next that is going to follow this is going to be the exponent of a negative 5, the vibrational temperature over 2T. And if we look at this specific representation, of course, this is going to go on, of course, up to the last representation for that, for various ranges of those energy levels. Now, if we consider this specific, of course, a linear equation, we're going to see that there's a specific constant term or that is going to be arising from this specific representation, and this basically can be factored out, which is basically the negative vibrational temperature over 2T, and negative vibrational temperature over 2T, and then of course we're going to remain with some common factors within this specific expression. Therefore, if I try to give that one in form of a representation, we're going to have a common factor factored out, given the exponential over this negative 0V or vibrational temperature, which is basically this is going to be theta V all over 2T, which is a common factor taken out, and then I'm going to have these other various ranges of expression given plus. So the multiple between this one and this one is going to give us the first factor, and then we're going to have the multiple between this one and this one giving us the second factor in that specific case, which is going to be the exponent over negative that specific temperature divided by T. So this is going to be T given as such, and then we are going to go after that one, go in that specific order, and then we're going to have the next given in terms of exponent over negative 2 vibrational temperature all over T. And that one goes on and on, and this is going to generate what we refer to as, of course, the geometrical progression, and of course which we can represent in a general equation in terms of perhaps a general representation. Now I'm going to have to do a substitution for this, and perhaps represent one of these common terms in terms of perhaps a known variable, so that we can be in a position of trying to simplify this specific expression. Now in this case, then therefore I'm going to write, so I hope we have understood this, or rather let me just put it at this specific point. So I'm going to substitute one of the common factors using an unknown value, so that we can come up with a general expression, whereby we're going to say let x represent the exponent of a negative vibrational temperature over T, And in any case, if we have n of these factors within this representation of our geometric progression, then therefore I'm going to substitute it with the x. And of course, this is going to lead to a general equation of the form. So I'm going to do away with this. So if I consider the last equation which I've come up with here, I'm going to have this one represent this specific case. And therefore, I'm going to come up with a general form from this specific expression, whereby QV is going to be represented as the common factor of a half, which basically is this specific exponent given in terms of this expression. But as we see, there is a half factor which is being given in this particular case, and this is going to cater for this. So therefore, this is going to be a common factor, and then I'm going to have the first term, and then the second term is going to be represented in terms of x. And therefore, I'm going to go on in that specific order, and therefore x to power 2, x to power 4. So this kind of progression, as I had said, is going to result in some kind of geometric progression, which of course we are going to have it ending up in a general description of the form x raised to power a half all over 1 minus x. And if we try to look at this, then therefore we can substitute, or rather replace back our representation for the value of x, and this is going to result in a form of the partition function represented as QV is equivalent to this specific factor, whereby we're going to have x raised to power a half still being represented as x b, and then we're going to have this factor as negative the vibrational temperature over 2T given as such, and then our denominator is going to be given as 1 minus, so the value of x, as I had said from that specific point, is going to be the exponent of negative this vibrational temperature all over T, and then this is going to give me a general, from using this specific perspective of perceiving this as a geometric progression which is of this nature, then I'm going to use this substitution. Of course, this is going to result in this kind of result of this geometric progression, and of course we can do a substitution back and obtain this specific kind of representation. Then therefore from this still we can reduce this one further or simplify it, and this is going to result in an expression or an equation for the geometric, the partition function, vibrational partition function, given in terms of the exponent of this specific part. So we're going to do a rearrangement, vibrational temperature over 2T, which is a positive. Of course, we have exchanged this exponent, and this is going to be given in terms of the exponent of vibrational temperature over T minus 1 given as such. So this specific representation, of course, is going to be giving the molecular vibrational partition function. And of course, we can be able to have this specific function over the molecular vibration partition function, considering this temperature being given in terms of course, the vibrational frequency, which we had, of course, given in our last statement. Now, we are given the relationship between the vibrational temperature and, of course, the vibrational frequency using this specific relationship. Therefore, if I'm going to consider the vibrational frequency being given in terms of this specific representation, this is going to be given in terms of the expression whereby we're going to have this the exponent of so I'm going to do a replacement of this using the vibrational frequency factor, and then that's going to be all over 2kBt, and then this is going to be over 1 minus the exponent of negative HW, this is omega not W, over kBt, and this is generally going to give me a final description of the representation of the partition functions in terms of this vibrational frequency. And this is how we can come up with an expression that is representing a harmonic oscillator in terms of a diatomic molecule, of course being represented as a partition function of this particular nature. We can see the aspect of this particular kind of energies being given in terms of this general representation. But of course, as we have been doing an evaluation of this this one has assisted us come up with a specific expression for giving this a specific vibrational partition function, of course, in terms of these vibrational energy levels. And this, of course, is going to form our last bit of this specific concept. Now, in our subsequent videos, we're going to look at the various applications of this particular formula that were developed over various discussions for the concept of partition function. So catch us in our next video, and kindly subscribe to our channel for various links of other similar videos which are going to assist us collaboratively in understanding these various topics. So that is it for now, guys. Bye, God bless you. Catch us in our next video.